So hi guys. So today I am going to talk about, tensor products. Not the actual construction of it. So not the actual construction, but a bit of motivation and insights here and there. What I learned about tensor products um, in module theory, of course. So yeah. So we will talk about general modules. Over R. Okay, not vector spaces and all that. So yeah. So. So let me start with, okay, so in this video I might stutter and say things, repeat things. So please forgive me for that. But we will start with tensor products first. About the motivation of the tensor products and why do we need tensor product and all that, and why is it so beautiful? Like the construction is also very beautiful and and the intuition behind tensor product. And hopefully I am able to, um, explain this properly. So yeah, let's start with let's start with uh, yeah. So I am not going to go through the construction of this thing because it's already in books and stuff. Yeah. So just the intuition and how, I mean, and why and all that. So so suppose we have a so let's start. Suppose we have a like R module M, right? So basically M is an R module. Okay. Now suppose we have a map. Let's just say we have a map from R to R dash. Both are rings. Okay, and we are assuming everything to be CRU, commutative ring with unity. Yeah, so, and this is a map. Now, I mean, as we can see that this is R dash is an R algebra, R dash an R algebra. Basically, it has both the structure of a ring and as a R module. Okay, so it has both the structure of a ring and R module, so it's an R algebra. So yeah, we can refer to R dash as R module. Now, M is an R module. Okay. Mm, Now, what do we want? Let's say we want to change the base of M. I mean, so suppose we want that we want to think of. Is there a way we from M we can get M dash such that M dash is an R dash module? Okay. So basically, we are changing the base. We are changing the base ring. Okay, M is an ARM module, that is fine and all. But is there a way we can, you know, we can change we can get from M to M dash with an R dash module while also preserving the relations of M, and maybe introducing new relations. Okay, can we do that? Suppose M has a very complicated structure. Okay, so like over a particular ring, suppose we change the base ring and like and we can deduce some properties from there. Okay, like because the old relations are preserved with addition to new relations. So and we can then come back, or we can, or the term is called descent. So we can descend from back from that M dash to M. Okay, and apply those properties. I mean, so we will be able to understand the structure of M in a better way, right? So this is where the actually the tensor product comes from. So if we get M dash as an R dash module while preserving the relations in M, also introducing new relations, right? So we can actually get an idea of the if the structure is difficult in M as an R module, you can get an idea of how, uh, like yeah. So so this is the idea. So basically, let me just write few things here. So right, and one way to do this is, a very natural and canonical way to do this is by using the tensor product, right? And because this is very common knowledge, if you do M tensor, so M tensor R dash, now R dash is a, as we can see, R dash is a R module. M is also an R module, but M tensor R is an R dash module as well, right? Because any R dash we take to M tensor R, right? We can define that this action to be M tensor R dash R, right? So this actually makes it a R dash module. So tensoring is very natural way to change the base of that ring. Okay. Now there is also something called so this is also known as let me extension of coefficients. Let me write this properly. Okay, let me just think it. Extension of coefficients, and also the very process of returning back, also the very process of like now this is an R dash module. Also the very process of changing the base ring from R dash to R or returning to R is also known is called descent. Okay, this is called extension of coefficients or base change, and the kind of like the inverse process is called descent. We will not talk about descent, flat descent, and all that. We will not talk about this here, but maybe some other time. So we will focus on this. So yeah, so the inverse kind of like the inverse process called descent. One very good example that you know I can actually think of is like this. So yeah, so we'll start with a we'll start with a linear transformation. I mean, not a linear, yeah, a linear, basically a matrix. We'll just take a matrix. We'll just take a, let me just mark this. We'll just take a matrix, let's say M n cross n R, right? Then we have a like map from Rn to Rn such that, right, x goes to a dot x. This is a linear transformation. We can denote it by T of a. Okay, so yeah, we don't need it, but yeah. So yeah, and and we know the characteristics. I mean the characteristic equation of a is nothing but determinant of a minus lambda a minus ix, right? Yeah. So that is one. I mean this is a characteristic. I mean let me write it properly. So determinant of a minus, I mean we can just use data as well here, a minus ixi. So this will give us actually the characteristic equation. Okay. Now what about symmetric matrix? I mean of course R is not algebraically closed, right? R is not algebraically closed. So no roots, I mean you also, I mean no roots might be available like of characteristic of CHAX, right? I mean I mean also roots are nothing but the eigenvalues, right? So basically roots of this, so everyone knows this, right? Roots of this are nothing but the eigenvalues lambda. So eigenvalues. Now suppose we want to find the eigenvalues of a symmetric matrix, right? So since R, I mean yeah, and also one more thing, R is not algebraically closed. Let me repeat this once again. So all the eigenvalues might not be available in this particular uh, this particular field. So algebraically closed, not algebraically closed. So now, suppose we want to find the eigenvalues of, symmetric matrix. Say A is symmetric, that is A transpose is A. Okay. So now one can think of doing this by saying, okay, now we can think of, Rn as an R module, right? I mean, of course, it's naturally an R module. It's a free module of dimension n. Actually, it's a vector space. So Rn as R module. Now we can extend the coefficients, right? I mean, so what about Cn? I mean, okay, just let me just say this. We can regard, I mean, we know Rn as an R module, right? All right. Now we know we naturally can include it in C, inclusion. It's a very natural inclusion into C. So is there a module M dash? Suppose consider this to be M. Is there a module M dash which is naturally a C module? I mean, yeah, there is Cn, right? So basically, so Cn. So it's nothing but, yeah, Cn, right? Cn has a C module. I mean, we don't need tensor product here because it's very easy to see because everything is free. Okay, we don't have any torsion element or something like that. Everything is free here, and we can Rn as an R module, and we have a an inclusion map from R to C, right? I mean, both are rings. So what is the like most like natural module like which has a base ring C? I mean, which has a, yeah. So it's Cn, right? So it's kind of, so basically we have extended the coefficients from R to C. Okay, it's kind of like that. So Cn as a C module. Now in C we can, in Cn we can define like inner product like this, and it's very uh, yeah. So x transpose y, and x and y are column vectors, right? Now one more thing. One more thing is, one more thing is, right, that A is, let's say A is A transpose here, right? A is A transpose here, basically in M, N cross N C, right? So now if we do something like this, Ax comma y, and that is very, like, these calculations are uh, not very difficult to do. So X transpose A, so yeah, compose Y bar, which is nothing but A Y bar, and which is nothing but X A Y, something like that. Yeah. So this we get, right? And one more thing, that since C is algebraically closed, C is algebraically closed. I mean, the, how should I say this? The I mean, it will have the characteristic equation of A will have all the roots in C, right? So every root is available because it's so, yeah. So every root is available. So basically we will have eigenvalue. So there will exist an eigenvalue, say lambda, say lambda, lambda. Now let's just say, and from that lambda, I mean, there will be a corresponding eigenvector. Let's just say it is, let's say y eigenvector corresponding to lambda. Now y comma y, I mean, they just say lambda y comma y is nothing but lambda y, right? This is nothing but a y, and this is nothing but y a y inner product, and that is y lambda y. Okay, so this is y, sorry, I'm so sorry, the scalar will come out, y comma y. So if this, I mean, both are equal, then lambda equals to lambda bar, which means lambda has to be real. Lambda is real. So this is how we can prove that all the eigenvalues of the symmetric matrix, real symmetric matrix, is real. Okay. So yeah, so this is a pretty nice example of how you know, extension of coefficients or base change through this map I, right, is very useful, right? And one more thing that is like, I mean, we need to be very careful of, that the characteristic equation of A in R, I mean, in the field R, remains same in C. So this is one invariant factor, right? This doesn't change. I mean, we are using, basically abusing the fact that this doesn't change to, you know, show that, of course, this, since C is closed, and yeah, so from there we can just do this basic inner product calculation and say that lambda is real. So this is a very good example of how, you know, like from the base ring we are changing to another ring so that it forms an M dash and R dash module, and while keeping the relations over like M constant, and while introducing something new. Okay, and then once again we are descending back into R, right? In this case, which is called descent. So this is one way to, you know, see that. Yeah. So, and yeah, one more thing. So I mean, this is also, I mean, if you use tensor product, this is also, and since R C, so we can regard C as an R module, right? C is an R module, then, and we can easily see that, tensor product commutes over direct sums, so this will be nothing but C to the power n. So yeah, that's what we actually did. This is a very natural way to, extension of, to extend coefficients. Okay, so this is actually a main motivation for the, I mean, I mean, of tensor product, and also how the bilinearity comes. So basically, from an R module M, okay, from an R module M, we want to make, oh, okay. Suppose we have this, let's say, map, let's say phi R dash. So we want to make an R dash module M dash. Okay, so it should preserve all the relations. So basically, the new m dash that we have, it should be, uh, I mean, now, yeah, we can define uh, multiplication in m as an R module, right? But not as an R dash module. But for to create m dash like as an R dash module, we need this to be linear, right? Because let's just say R dot, let's say m, right? So it should be linear. Uh, this is already linear now, R dash. So we want to create a module m dash where this is possible. Okay, so and also this should be linear in R dash, R1 dash plus R2 dash. Okay, so m, so this will be R1 dash m plus R2 dash m, and also R1 dash, so and also it should be linear in m as well. So m1 plus m2, it will be R dash, this will be m1 R dash plus m2 R dash, and also it should be, like be compatible with R. Okay, so R M R dash, which will be M R R dash, something like that. Okay, so yeah, so and this is nothing but exactly the conditions for bilinearity. That is this, right? Mm, that is M times dash to M dash. This should be R bilinear. Okay, this should be R bilinear, and from here we can see like, and so what do we want? Now we want to, so basically, so we want such m dash. So how can, how can we achieve this? How can we get such m dash, right? So basically, what we can do is, right. So we can gain all the, we can get all the R bilinear. Okay, T here is an R module. We can get all the R bilinear maps. Okay, we can get all the bilinear maps, and if we can find such module m dash, which factors this, okay, right, we will be able to get the, that unique m dash that we are looking for, right? Instead of guessing what m dash is, we look at all such possible R bilinear maps. Okay, and then from there we get a universal one, meaning that if we have any R bilinear map, it will factor through m dash, and that is nothing but the tensor product. Okay, that is nothing, and m dash here is nothing but the tensor product. Now, yeah, so this is uh, and now we can generalize this very idea about tensor product, right? So if we have m cross n and we have a bilinear map to A, we have a bilinear map to A. Now we can actually, we can actually factor, so here let me write here T. Now T is the tensor product for any bilinear map we can uniquely factor, right? And let's say this is phi. So T comma phi is referred to as the tensor product. So yeah, yeah. In this case, the universal property holds. Like any map we have, um, so each bilinear map to some R module A, there is a unique R linear map T, okay, such that, yeah, so this commutes, okay. So this is nothing but the tensor product. Now I am not going into details of constructing tensor product. So let me give you one more example of base change. Like let's say R is any ring, so R by R is any ring. So basically we have R by I, uh, projection map, right? We have a projection map. Now say R M is an R module, okay? R module M. Now we want to make from M dash, which is an R by I module, okay? So we are changing the base from R to R by I. So basically, and we know this is actually very, um, very like popular result. So basically, if we tensor it with R by I, so this is isomorphic to M by IM. So tensoring is the only way we get the nearest module, like we get the nearest module to M, which is also compatible with this R by I structure. Okay, right. So this is also one pretty nice example to think about. Like, yeah. So, I mean, this is not exactly extension of scalars here because this is a smaller ring. We can also think of it. I also, I mean, so we can also think of it as a base change or base change along pi, the map pi, things like that. So, yeah. I mean, this is, I mean, the terminology. I don't know why. I mean, I can understand why it's called extension of scalars, but not in. I mean, yeah, this case because it's like changing the ring along pi, changing the base ring along pi. Okay, so yeah, so this is one way to think about this. One another way I would like to talk about is the the representable functors. Okay, I mean, so basically, by the way, so basically we have if we have R mod, right? Like we have R mod. Hmm, R mod is a category of all R modules to R mod. Okay, we have this functor bilinear m comma sorry m cross n comma dash. Right, so basically it takes any module R module A and it maps it to bilinear m cross n comma to this. Okay, sorry, to A. Now this is an also like an R module. This is also an R module and A is also an R module. Okay, so this is actually a functor, and we can check very easily that this will be a module. So this is actually a functor. So when we talk about all such maps, right, right, I mean to A, right, I mean all such maps, all such bilinear maps, this all will belong to this bilinear, like this functor, right? So now, so basically, any map we have, any map we have M, we can factor through M tensor N. I mean, we can factor through this, we can factor through M tensor N. And if we even change B, right? So if we even change B, that doesn't matter. Like because for any R module B, for any R module, like this by the universal property, this is actually like M tensor N, this map we can factor through this. Okay. So basically, and one more thing that this bilinear, I mean, we want to capture the bilinearity, I mean, in a module. I mean, from bilinearity, we want to, I mean, go into linearity. I mean, one way to also think about tensor products, this is another interpretation, is like, I mean, we want to work with a like module where it's, because I mean it's bilinear, this is fine, okay. This is also a module, this is fine. But we want a single object, I mean in this R mod category, such that which how should I say this? It represents the functor, right? Okay. So I mean, yeah, I mean suppose we have a right. Suppose we have m cross n to A and given by the map B m comma n bilinear map, right? Now we can fix m and vary n. So this will be all maps from A like this n to A, right? So in some sense this so basically this is known as currying. This term is called currying. Basically what we do, we change the bilinearity into linearity by fixing a particular coordinate, right? So and this is very intuitive to see, and we can also see that I mean, this is very intuitive that m cross n, and we can also prove this. Sorry, let me write A is isomorphic to m home in comma A, right? So this is pretty easy to see, but this doesn't capture this whole function in a single object, right? We want something, right? I mean the structure, I mean this structure may be complicated, right? This structure may be complicated. We want to study this functor from R mod to R mod. This is a bilinear functor. Given any given any object A in the R mod, it spits out an object in the R mod which is nothing but we want to study this. To study this, we want to capture this in a single object. Okay. Okay. And the very fact of capturing is known as the representing object. You want to capture so that it is easier to see. I mean, it is easier to study the structures or the properties of this. Okay, right. So one way to do that is using the tensor product, right? So I mean we will prove it that this is isomorphic to home m tensor n comma a, right? And this makes sense because this is the universal element, right? So 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 if we study this set, which is easier to study actually, we will be able to, you know, get information about this. So basically we are capturing bilinear this functor, okay, right, through a single object m tensor n. To study this, if we can, to study this functor, all we need is this to know about m tensor n, right? And we can use the home functor to I don't think I'm making this very clear, but yeah. So let me actually now define the what is called a representative functor and representative object. So that is actually mean, so a functor f from a category to a set is said to be is said to be a representative functor, okay, if it is isomorphic to home, because we might not know the properties of, the functor, or or maybe it might be very difficult to study. So what we do is we capture it through a home functor, right? And home is actually a by I mean so this, and this A is known as the representative. It is naturally isomorphic. So I will define what naturally isomorphic. It's basically a natural isomorphism where each component is isomorphic. So natural isomorphism where each component is, sorry, natural transformation where each component is isomorphic. But okay, so A is here the representing object. Okay. So basically we want to so from here. Um So basically, to study this, I mean, to study this, functor, okay, all we need is, information about this representing object. If we get this, we can get home, because home is a function from R module to set, and we can get the relevant information about this. And this is also the basis for uh, unit lemma, which is nothing but uh, right, natural transformation between home and this natural transformation, this is naturally isomorphic to f of a. So this is, we will not talk about this, but this is called the unit lemma. uh, so yeah, so in this case, our our tensor product of n tensor n is actually a representation object, and it represents this functor. Now we will show in the next page that uh, this is isomorphic, okay. Naturally, sorry, isomorphic, I mean both functors are isomorphic, natural isomorphism. So let's just so yeah, we will show here that this is isomorphic. I mean naturally isomorphic. I mean naturally isomorphic. So we will show that. So for to show that they are naturally isomorphic, we need to show that a natural isomorphism, and each of the components are they are isomorphic. Okay, so let me just start with A to B. So let me, yeah. So let's say, okay. So this is an R module. This is an R module. I'm not writing. So everything now I'm talking about, it will be from, every functor will be from R mod to R mod, category of R modules. Okay, let me write it properly. Yeah. So from A to B. So basically this will be F. So let's just say this is alpha. Okay, it's a R module homomorphism. So basically we have this, right? And first we are applying this functor home m tensor n. So basically we want to show that these functors are naturally isomorphic. Like let me write it here, home m tensor n, this is isomorphic to bilinear m cross n, this, right? We want to show that they're naturally isomorphic. I mean, yeah. So let me write it first, then I'll try to explain. So So basically, and this is nothing but bilinear uh, m comma sorry m cross n. Okay, this is very let me write it properly. Let me write it properly. This is bilinear m cross n comma this. Now A, since they are functorial, like both the functors, of course, they are functorial. So, so this A, B, they will be, they will go to home. M tensor n comma A to home. M tensor n comma B. So this map, with the help of this map, home M tensor n comma F. Sorry, alpha. Sorry, I'm so sorry. This will be alpha, and here this will be bilinear m cross n comma a to home m cross n comma b. Sorry, this will be bilinear m cross n. Bilinear m cross n comma b. Now say this is eta a and say this is eta b. Now if we want to show that there is a natural transformation between these two functors, okay, then we want to show that there is a natural transformation between these two functors. So, uh, uh, I mean, first we have to show that there is a natural transformation. By that I mean this square will commute. ठीक है? So, yeah, right. Now, and also that each of this component, eta A and eta B, they're isomorphic. And they are very easy to see because home m tensor n comma A and bilinear m cross n comma A, we already know they're isomorphic, right? There, I mean, we can take a map here. I mean, this is pretty easy to see. So I am not going to show this here. All I'm going to show that this square commutes, that this is a natural transformation, and in any book we can get that I mean, this is a very standard proof that they are isomorphic. Okay, we can take a map, we can I mean, we can take its image, and then we will have to take the inverse image of this, and we can easily show this. Okay, I actually forgot to write this. This will be bilinear m cross n comma alpha. Right. So let's let us take a element f. I mean, I'm writing to saying f, and let us take an okay. How to write f? Yeah, let us take a f from this, right? Home and so we take f here, and so let me write it here. We are taking f here, right? F will map to eta af, right? And f will map to eta af. Okay, so and and what is eta f here? Eta af, this eta af will belong to this, and eta af of m comma n, because right, this is a mapping between m cross n to a. So this will be defining as a m tensor n, and we can check they're all well defined and all that. So f m tensor n, right? Okay, and this is very easy to see because we take any morphism from m tensor a to a, and we are mapping it to this morphism. So and I mean, so what is eta a is nothing but f of m tensor n, right? So and similarly from here, if we take a morphism here, we can go back here, right? Okay, let's say we take something like g, and eta a inverse g will be g of, I mean, m tensor n, right? Yeah. So yeah, but I mean, that is easy to show. So we will only show that this square commutes. So actually, let me divide it into two parts: the upper half part and the lower half part. First, we do the lower half part. So this same tensor n from eta af, this will go to this will go to alpha eta af. And why is that so? Because I mean, we have a map from m cross into a, right? Okay, and this is what is this? This is eta af, right? And there is a map from a to b, alpha. And what is a map from m cross n to b? This will be alpha composite af, right? Very simple using this bilinear since they are functorial. So right, so this is this. Okay, now let us worry about the like upper half part. And what is upper half part here? Upper half part here is f will map to uh, yeah, this is recording. Okay, f will map to so this is f will map to similarly in a similar fashion alpha compose f, right? I mean, through with the help of this, because this is simple. This is simple, very simple, that m to a and a to b is like alpha. This is f and this is a alpha compose f, right? So, and since it's a home covariant functor, oh, before that, let me tell you that home is actually a bifunctor. Okay, so this is actually a map from C op to C to set. This is actually a bifunctor. So this is contravariant in the first coordinate, this is contravariant, and this is covariant in the second coordinate. So yeah, okay. So this is basically becoming a composition, right? So I mean basic properties of home functors. So this is very easy to check. Mm, So, and from here, this will map to eta b of alpha compose F. Right? Now, if we can show that both of these maps are equal, then we are done. Then we can show that they commute. And to show both maps are equal, we need to take elements. So first, let me check eta b of what is alpha comma F m comma n. And we know what is eta b here. So this is eta b. So we right, so this is alpha comma f, this is a map here, and we are then then we are applying eta b to it, composing with eta b. This will actually result in alpha compose f m tensor n, right, which is nothing but alpha of f m tensor n, right? And this is the same as this, because alpha eta af is nothing but alpha f m tensor n. So both of them are equal. So this diagram commutes. So this diagram commutes. So there is a natural transformation, and we can see that, I mean, we can easily find the eta A inverses of each other, right? We can easily find the inverses of each other. So eta B inverse. So basically they are naturally isomorphic, right? So basically M tensor N is a representing object representing object, okay, of this functor of home, sorry, of this bilinear functor, bilinear m cross n to, yeah, this functor, which is from R mod to R mod. This is one way, or this is also one way to see what the tensor product is. So yeah, I hope this video was, I mean, yeah, it is too lengthy, but yeah, it is what it is.